So, we have a long weekend, which I hope everybody had a pleasant one. We come back to this weather, to how cold it is. Whose fault is that, by the way? You might be one of these. Trevor, how cold it is? Okay. And then, on top of that, the heat's not working in here. So, yeah. So, I will try and make class as expeditious as possible. I'm still working on the exam. All honesty, it'll probably be another week or so before I get it finished. Just a heads up. Okay, I'm moving this back here. This beach ball.
It's not the way.
It's not mine. I'm just getting it out of the thing.
Talk to it like you deflated it.
They use it for you.
Yeah, I was sitting over there. You just deflated it.
Okay. I do have good news, though, in the realm of homework. I don't have a homework for you today. So, you don't have to be that happy about it. No, today is very content heavy, and I want you to just sort of absorb what we're talking about today so that we can start using it next time. Assuming that we're here on Wednesday, because I know we're supposed to get hit again with some more heavy weather. So, we'll see what happens. I'm usually, I've got homework set up and ready to go. I usually have them uploaded well in advance on Blackboard, but this time I don't, and that's probably a good thing because we might not, who knows, we'll see what happens, so, with school. All right, did everybody get the code? Did you get it? Okay. So today we're going to talk about bolts. That's our goal for today and for the next, 5 lectures is bolted connections. And what we're going to try and review today are 2 limit states related to bolts, bolt shear and bolt bearing. Let me talk a little bit about bolts, and I brought the bolt assembly with me. I'm going to pass it around if you want to take a look at it. So whenever you see a structural bolt in the field, you will typically see 2 markings on it, okay? So the first is related to the ASTM specification that it must adhere to. So in other words, some very common ones are ASTM A325, ASTM A490. The difference between the 2, those are the 2 most common bolts we use in structural engineering. The difference between the 2, A490s are a little bit more expensive, but they're also stronger. So the idea is that you pay more per bolt for the 490s, but you can use less of them, is sort of the idea. But A325s are probably the most common that you would see in building construction. 490s, probably a little bit more common in bridge construction because of fatigue applications and splices and things like that. These bolts and the bolts that are getting passed around were made by Nucor, hence the little N logo there. Now, I need to prepare something right off the bat. So, these A325 and A490s, those are the ASTM specifications that those bolts adhere to. I imagine if everybody in here has had CE321, you know what I mean by ASTM specs, because you've used ASTM specs for things like cylinder tests and all that, right? Well, here's the thing. There are other bolts that share the same material characteristics, so the same strength properties and things like that, but they follow different ASTM specifications. So a good example of that are ASTM F1852s. These are what are called twist-off control bolts. So we'll talk about this later when we get into the land of slip critical connections, but the idea is that, so these are really, really common in bridge engineering and in areas where you need to design a slip critical connection. We'll get to what that means here in a bit. But the idea is that you use this really special wrench, and what it does is it grips both the nut and the bolt on this little splined end. And so you don't need, like, think about, you know, when you're tightening a bolt, you have wrench, and you're doing that with both hands. You don't need that with a twist-off control bolt because the single wrench grips both the bolt and the nut all from one end, right? It twists it, gets the required pretension, and when it hits the required pretension, this little splined end sort of chucks off. And so it's great for inspecting bridges in the field and what have you. Here's the thing. They follow the same strength characteristics, but they follow a different ASTM spec. So what the manual does, what the steel manual does, is it breaks these different classes of bolts into these groups, okay? And so the most common ones we'll use are group 120 and group 150. But you'll see in the manual, there's also group 144 and group 200 and whatnot. I want to be clear, there is no such thing really as a group 120 bolt. What AISC has done is they've grouped together a bunch of bolted products that all have the same properties and lumped them together for the purposes of the spec. So I needed to explain that right off the bat when we start seeing this in the spec, that there's no such thing as a group 120 bolt, but there's a bunch of bolts that have the same properties. Make sense? Okay. Okay. Now, in order to explain how we go about analyzing and ultimately designing bolted connections, what we need to do is take a look at what I'll call a bolt assembly, okay? And so what I mean by a bolt assembly is we're talking about, you know, a bolt, the nut, the washers, and also the two parts that we're joining, right? The whole idea behind a bolted connection is you're joining part A to part B. Now, okay, I have a bolt through some plates, and I tighten the nut. What happens to the plates? So here's a plate, bolt goes through them, and I start tightening the plate, or tightening the bolt. What happens to the plates? They smash together, right? Okay. And then once I have this connection together, I can then take this connection and yank on it, apply bending moment, shears, what have you, right? So what I would propose is that when we're looking at a bolt assembly, we're going to have whatever loads the connection is subjected to that are being applied to it. So we're going to apply some load to it. But we're also going to have, and it's kind of hard here on the screen, my apologies, I don't know why it's coming up so faded. But we have these, I've got these blue arrows here and these blue arrows here. What those are representing are the whole, this part. When you have a bolt going through two plates and you tighten the bolt, the plates are going to smash together. Okay. So then I've got the plate, I got the bolt through it, and I start yanking. Okay, what happens? Well, the connection is obviously going to want to resist those loads, right? It's going to want to prevent the connection's not going to want to fail, right? So how does a bolt assembly resist load? Okay, and I propose, so we know how the loads are applied, either applying the load or through this, smashing the plates together, but how does it resist load? Well, think about the different ways that a bolted connection could fail. Okay, well, and two of them are pretty easy to understand. So if I have a plate and I have a bolt through the plate and I'm yanking on it, I could shear through the bolt, right? I could just shear the bolt right in half. Okay? So that is one resisting mechanism in the connection. The resistance from the bolt just being in shear. Okay, so that's one. Now think about it like this. Okay, so let's put, actually let me see if I can, I don't have enough room here. Let's do it. So here's the bolt, and let's say here's the plate. Okay, so I'm yanking on it, right? That's not centered at all. That's a little better. Okay. Now, first off, we know that there is a hole in the plate that the bolt has to go through, right? Okay. I'm going to exaggerate the dimensions of that hole a little bit. But as I'm yanking on the plate like this, would it be fair to say that the hole maybe kind of looks like that the bolt is actually coming into contact with the edge of the hole, right? So, like, here's the bolt, here's the bolt, here's the bolt hole, and then as I load, the plate's actually coming into contact. The bolt is bearing on the plate. Does that make sense? Okay. So, one resisting mechanism is the bolt just wanting to shear in half. The other is the bolt coming into contact with the plate, and maybe the plate resisting that load until it fails under those bearing stresses. Okay? So there's two resisting mechanisms, bolt shear and bolt bearing. Now what about the third? Well, if I have two plates that have been sandwiched together, okay, and I'm pressing those plates together with some sort of normal force, and then I apply a force like that, I seem to remember that I can relate lateral forces to normal forces with a coefficient of friction, right? I'm going to have plate contact with other plate, and there's actually going to be friction developed between these two surfaces, right? If we adhere to certain conditions, and we'll talk about this a little later, we can actually count on that friction for the purposes of design. And there are a couple of, of arenas where we actually do need that friction. Bridges are one, sometimes earthquakes are another. So because of that, we have these three force resisting mechanisms. And because of that, what we do is we split bolted connections into two main categories. In other words, we have bolted connections that are designed as bearing type connections and bolted connections that are designed as slip critical connections. So a bearing type connection, the load is transferred by bearing on the bolts. The bolt goes through the plate, you load, and the bolt comes into contact with the plate. With a slip critical connection, we say, well, before that happens, we actually get that friction between the two plates, and that happens first. Okay? We'll deal with slip critical connections later. Most of our time is going to be spent on bearing type, but I wanted you to kind of get an idea of the load resisting mechanisms. Everybody with me so far? Okay. Okay. So, for bearing type connections, we have two different limit states that we really need to assess. We have the failure of the bolt or the failure of the plate. Okay? The bolt, in this case, would fail in shear. The plate, it can actually fail two different ways, and the best way of describing that is to just show you. And I got an image on that here a bit later. But for each of these limit states, we're going to have a phi RN. So it's going to be like tension members. We have a phi PN for gross section yielding, a phi PN for net section fracture. Same idea here. A phi RN for bolt shear, a phi RN for bolt bearing, and we just take the minimum. Okay. Now for bolt shear, we're going to go through the math, but we got a really handy guide in the manual that's going to make our life a lot easier on that. The other thing, and we're not going to talk about this today, we also are going to have connection layout requirements that we have to adhere to. That'll be a topic of discussion for Wednesday, if we're here. Okay. So let's talk about bolt shear capacity. Let's talk about that first. Okay. So what we're concerning ourselves with right now, here's a bolt, and we're loading it in shear. How much load until we just shear the bolt in half? How do we get there? Okay. Well, what we're going to come up with a pretty easy equation to calculate that, But what's going to get tricky are the thread conditions and the number of shear planes. So let's deal with the simple part first. So how do we calculate the shear strength of a bolt? Well, we take the nominal shear stress and we multiply it by the area of the bolt. By the area, we're talking about the nominal unthreaded area, or just, in this case, now we are talking about the area of the bolt, so pi over 4d squared. Okay? Now, what's going to make this tricky is, again, the two looming questions is, are the threads included in the shear plane, and how many shear planes are present? And you're probably not 100% what I'm talking about there, but that's why I have pictures. Okay. So here's what I mean when I say that the thread's included in the shear plane or not. Okay. So I've got a plate bolted to another plate, and I have a bolt going through the two holes, and I yank on them. Now I'm curious, which of these two is weaker? The one on the left or the one on the right?
Left.
The left. Why?
Because it's going through the threads.
Because it's going through the threads. The threads are weaker, okay? So we engineers are very creative with our naming schemes. And so if I had like group 120 or 150, I call it group A here. But if I had group A-N, that would be threads included. Group A-X threads excluded. I'm going to use that notation throughout the next few lectures. So if I say group A-N or group A-X, that's what that N and X means. Okay? Now, by the way, if I didn't tell you whether the threads were included and excluded, what should you do? Do you assume included or assume excluded? You would assume included. Assume the worst. What?
Why would you design like that?
That's a great question. So that's a fantastic question, actually. So what you're saying is, like, wouldn't you have control over that? This will become a little bit clearer later, but because design is fairly iterative, where you're changing the members, the connections, the plates, like all throughout a given project, at some point it's easier to just make an assumption right off the get-go and then edit later. And I'm saying at the very beginning, that's what you'd want to assume. That's what I'm saying. The other thing to consider is that, I mean, you have to also ensure that the bolts are available. Like, in other words, for example, 3/4 inch bolts, you're going to have some distance here. Is that distance matched up with the plate thickness? You know what I mean? So, all right. Okay. Now, we're not going to look at this table very much, but we are going to look at it today. So, what I have here, so I want everybody to turn to this. This is on 16.1-137. I got to say, they did a much better job organizing this table in this manual than they did the last one. That may be a hot take, but I like this table a lot better than I do the last manual. So, let's go back to our PRN. Okay. So this is how we're going to compute the capacity of a bolt in shear. Okay, so we're going to take C, which in this case is 0.75. This pi over 4d squared. Then F and V. Okay. So what's the deal with F and V? Well, that's going to basically be our material characteristics, sort of like Fy and Fu. But we're going to have different values depending upon whether or not the threads are included or excluded. For example, group 120 bolts. If the threads are included in the shear plane, FNV is going to be what? 54 KSI versus what? 68? Does that make sense? That the threads excluded has a higher capacity? Well, of course it does, right? The bolt's stronger, okay? Now, I told you, I said we're not going to use this table much anymore. Trust me on that, and you'll see what I mean. But I want you to keep that table open for now, because we're going to do a quick calculation, and then we'll probably hardly look at that table again. And you'll see why. Okay. I'm getting ahead of myself. Okay. So like I said, there were two questions. Are threads included in the shear planes or excluded from the shear planes? But then the second question is, well, how many shear planes are there? Well, there could be one shear plane. There could be two. I mean, there could be three. There could be, 100 of them. But single shear or double shear is the most common. Now, if you had, so I'll say this bolt is in single shear, this bolt is in double shear. In double shear, that bolt on the bottom, I propose that its capacity is double that of its partner in single shear. Now, when I say that, what I'm talking about only is the bolt shear limit state. Now, did the bolt magically get stronger just by being in a different connection? No. What I'm saying is that in order to fail this bolt in shear, I must rip through twice as much material. So, in other words, what I'm saying is the difference between this and this is that I'm multiplying that by 2. The area is getting doubled. Does that make sense? Okay. Let's practice this. Okay. What is the design resistance of a 3/4 inch diameter A325 bolt in single shear, assuming that the threads are excluded? All right. So let's walk through this together. This is a really simple problem. Okay. So the bolt diameter is 3/4 of an inch. So the bolt area is going to be what? I might need some help on this. That sounds right, 0.442. Okay. Now what about its shear capacity, or its shear, its allowable stress? Well, it's group 120. Is it group 120N or 120X? So, if that's the case, what is its FNV value? 68. Okay, therefore, its phi RN is going to be this. Now notice I'm using a lowercase r because I'm going to start throwing that notation out, because the lowercase r is going to sort of be a capacity per connector, and then the connection capacity is going to be that times the number of connectors, if that makes sense. So, So what is that? And we'll just say 1 decimal place. We don't need to get fancy past that.
22.5.
Do I have a second? Okay. And notice what I've said is that's 22.5 kips per bolt. Okay? Now, that's not very difficult, is it? But it would sure be nice to not have to do that for literally every problem that we work on in this class. Okay? Everybody got this? So what I would like to turn your attention to now is this. Okay? Like I said, this table that we returned to, this table J32, I said, yeah, it's nice, but we probably won't use it much anymore. And the reason is because of this. Okay. This is table 7.1. I want everybody to turn to this. This is a much more important guide than what's back in the spec. By the way, if it's not clear from what I'm intimating, this is one you tab, by the way. I would tab this one. That one was already tagged, see? What I tell you, it's important. Okay. For this one-page table, the amount of info baked into it is really kind of nice. How do you use it? Well, it's pretty easy. What did we just look at? What group were we just looking at just now?
120.
Okay. Thread condition. Okay. What was is it single shear or double shear? Okay. What was the bolt diameter? We'll look at that. So it takes a lot of repetitive math and just does it for us. Okay. So I'll say this, like, I do want you to kind of understand how to compute the capacity of a bolt, but like in bolt shear, but I'm not really going to ask you to do it, because that's what this is for. Okay. So when we start doing bolted connection analysis and design, we're going to make incredibly heavy use of this guy. Okay. So have it tabbed, have it noted in your manual. We're going to use it quite a bit. Okay? All right. Any questions? And again, we're using the blue numbers, not the green ones. Okay. All right, so that is the connection, or the capacity of a bolted connection if we're looking at the bolts in shear. Now I want to look at the plate, okay? So what we've got is a bolt going through the hole, and we're dealing with connections where the bolt comes into contact with the edge of the plate hole and bears on the edge of the plate hole. So how can the plate fail? I propose that the plate can fail 2 different ways. And I've called those bolt tear out and bolt hole ovalization. Okay? So bolt hole tear out, what happens is you sort of get this like fracture tear along the edge of the hole, and it's the best way of describing bolt tear out is it's sort of like a mini block shear. Instead of ripping a whole chunk out of the connection, we're just talking about tearing the edge of the hole where the bolt's coming into contact. So it's more of a fracture style phenomenon. Ovalization's a little different. So with ovalization, what's happening is the bolt is coming into contact with the plate, and instead of fracturing it, it just sort of plastifies it, goes past yielding and plastifies it, and it sort of mushes the plate up near the hole, and you get this sort of hole stretching type effect, and it just sort of mushes up. Okay, and so we call that hole ovalization. The equation that we use for that is very empirical. Okay, but let's get into it, into the details. Okay, now I got a lot of spec here that I'm going to kind of distill for you. So let me do my best to sort of, break this down. So we're in Chapter J when we start looking up a lot of the specs here. So Chapter J has a section on welds, a section on bolts. So that's J3. So if we go to the section on bolts, we go to the various different, limit states that we're looking at, and go to 11, that's bearing and tear out. We say, okay, let's look at that. We've got oodles and oodles of different things to consider. So we go to 11A, what do we got? Snug, tightened, or pre-tension, high-strength bolted connections. So this will make a little more sense when we get into slip critical land, but the difference between a slip critical connection and a bearing connection is the degree to which the bolt is tightened. And a bearing type connection is just considered snug tight, just regular everyday tightness, nothing with any precision to it. That's where we're starting first. When you get into each of these expressions, the manual asks, do you consider deformation at the bolt hole a design consideration? We're going to in here. Most structural engineers that I know do. So we have two limit states, bearing and tear out, or bearing is the ovalization or the tear out. We get these two expressions here, and so that's where this comes from. So that last slide was me just sort of taking the spec, breaking it down. Here's what we've got. Okay. So our nominal resistance of a bolt according to the bearing limit state, looking at the failure of the plate, is going to be the minimum of these two. Now, I got to imagine that other than one term, everything here you've seen before, right? We've seen a bolt diameter, seen the thickness. The thickness is whatever material the plate is going through, or the thickness of the thickness is if we're talking about the bolt going through this plate or a flange or a web, so the thickness is whatever the bolt's going through. Our phi value is 0.75. The one term that's new is this one, LC. That one's different, okay? So that's, let me say this. It's not hard, but it does take some details to go through. But everything else should be pretty straightforward. And by the way, phi, in this case, is 0.75 as well. Okay. All right, with me so far? So what's the deal with LC? Okay. So LC is what's called a clear distance. Okay? And by clear distance, what I basically mean is edge of plate to edge of plate. So in the case of this bolt here, I'm talking about this distance. In the case of this bolt here, I'm talking about this distance. So by that very reason, I need to have a clear distance for interior bolts, and I need to have a clear distance for edge bolts. Okay, and I'm going to have a different formula for each term. So how do I calculate LCI? What's going to be the bolt spacing minus a hole diameter, because I'm going to go half a hole, half a hole. Does that make sense? For the edge one, I have the edge distance minus a radius, or half a diameter. Okay? So fortunately, the edge distances are pretty easy to calculate. Now, this next part is going to frustrate you, and I'm sorry, but I can't really do anything about it. When we were looking at tension members, let's jog our memory. We took the bolt diameter and added 1/8 of an inch. Why?
More material mistakes.
What's that?
For material error.
Well, you're half right. Let me ask it this way: did we add 1/8 of an inch, or did we add 1/16 of an inch twice? And now, what were the two reasons for the 2/16? One of them was what you said: damaged material around the connection. What was the other reason? Clear. In other words, so you have to actually drill the hole a little bit larger than the diameter of the bolt. So here's my point. One of those 1/16 of an inches was to reflect the actual dimensions of the hole. The other was just a little correction to account for the ability to transfer load to the rest of the member, which made sense if we were looking at tension members. We're not looking at tension members right now. We're looking at bolted connections. So in this bolted connection section of the class, we're going to be adding 1/16 of an inch, not 1/8 of an inch. I know, that's annoying. I'm sorry. But yeah. That's a detail you got to sort of just wrap your head around. Don't worry, we're going to have some practice on that in a bit. Okay. When I say edge bolts, by the way, edge bolts versus interior bolts, edge bolts are the ones that are, so they're sort of the opposite of the lead line. So the lead line would have been here, but edge bolts would have been ones here, because if we're talking about tear out, they're tearing out this way. So these edge distances are different than all of these. So whenever we're looking at a bolted connection, we typically look at a capacity per bolt, and then we multiply by the number of bolts. But what we'll do for bolt bearing is we'll take the capacity of an edge bolt times the number of edge bolts, plus the capacity of an interior bolt times the number of interior bolts. So just to give you an illustration, in the case of this problem has 4 edge bolts and 16 interior bolts. So just to give you kind of an idea. Okay. And then one final observation. So, excuse me. So, if you go back to this expression is looking at bolt tear out, bolt ovalization. And you're just taking the minimum of the two. The tear out, that 1.2 is not a 1.2. It is a 2 times a 0.6. Because what's happening, let's see if I can do this. Okay, so I'm yanking on this. Here's the bolt hole. We're talking about the ability of that shaded region to withstand tear out. Okay? So what is the area of that shaded region? Well, it's going to be the clear distance times the thickness, and then times, here I'll erase this, times 2, because there's 2 of them, right? There's going to be a tear out over here and a tear out over here, because the connection's going to want to tear out like here and here, right? But when I say tear out, how is it going to fail? It's going to fail in shear. So if it fails in shear, don't we need to multiply this times a 0.6? Is that a factor of safety, by the way? No, that's not a factor of safety, okay? Remember, elements that are subjected to shear cannot resist as much load as elements that are subjected to tension. They can only withstand about 60%. of what they're subjected to in tension. Does that make sense? Shear capacities are less than tensile capacities because of the mechanics of ductile materials. So, just throwing that out there. Okay, any questions? Like I said, I'm not giving you homework today because I threw a lot at you, okay? And I just want you to absorb this. What we're going to talk about next time is we're going to do a full-blown analysis of a bolted connection. But there's one thing we haven't talked about, and that's the layout requirements for a connection. How far apart bolts can be spaced from each other, how far apart bolts can be from the edge of a given plate. That'll be a discussion for Wednesday. But that's all I got, everybody. I'm going to pull up the code one more time, but I will see you all on Wednesday if we have school.